Okay, I'm back.
Welcome back.
Well, let's see whether my Mac is happier.
Yeah,
Aha!
perfect.
Very good. I find this always funny that I have to completely restart the application in order to get this going. Oops, okay. Oh, then it gets smaller for you guys as well?
Yes. Do you want to try it back and forth, like going back and forth? Because I think that was a problem with one of the speakers earlier.
Okay.
Okay, that works as well.
Yeah, it is. It is too.
Okay. Then I
Yes.
think we're ready to get started. So welcome back, everyone. I hope you've got some coffee or any other thing to get you over the post-lunch fatigue. It's my pleasure to introduce Professor Sven Bodo Scholz. And Sven Bodo has been professor at Heriot-Watt for more than 10 years before now moving back to continental Europe, more precisely Nijmegen Radboud University. Fairly recently. And as Charles said in the introduction this morning, I think a lot of you will know Sven Bodo from his work on single assignment C, but he's also done a lot of work on type systems more generally, memory management, generic programming, and partial evaluation. And today he's going to hopefully answer the question whether functional high-performance computing is the key to low carbon computing.
Yeah, thank you very much for having me and inviting me to give this talk. And when the two of you approached me and said, "Oh yeah, why don't you talk a little bit about your experiences in SAC?" I was wondering, should I just talk about the stuff that we've been doing and where this is all heading, or And then I started thinking, okay, it has been quite a while that I've been working actually on this, and why don't we have solutions yet, or do we have solutions yet, or do we need to invigorate our motivation? And I had a very nice chat with a colleague and good friend from Glasgow University, Wim van der Bavede, just about 2 weeks ago, and we were talking about low carbon computing. And I think this is a wonderful motivation, and I just have to share this with you. So if I say low carbon computing here in this context, what is it I mean? Do I mean FPGAs? I mean, everybody is thinking of FPGAs when talking about, low energy and things like that. No, actually I don't, or at least not exclusively. What I really mean is low carbon in the sense of energy consumption. Right, and in particular, I think we should sit back for a second and have a look at how our computing industry affects carbon emissions through the use of energy. And one of the things that we all know is, if you have a supercomputing center, like indicated by the picture at the bottom, these beasts are performance hungry. And if you speak to the people from, I call them the black belt hardcore HPC people, they when they talk about their exaflop systems, and they are wondering how many energy power stations they need next to the compute center in order to make this happen. But that's not all. We also use a significant amount of energy to produce the gadgets that we have. And this is not just supercomputers. No, actually, supercomputers are very small in that. But it is laptops, it's the machines that we have in daily use, and it's IoT as well. It's mobile devices. They all want to be programmed, and they all want to be produced, right? And so why is that such a problem? We are going to use energy anyways, right? We are shifting our cars to energy. So why would computing actually really matter? Okay, let's have a little bit more of a look into this. So I know this may seem a bit off topic, but please do stay with me. So here we have what is called the emissions gap, and I stole this from a UN report, from the emissions gap report of the UN from 2020. And what you see here is, can you see this cursor? Oh yes, you can see the cursor. That's fantastic. you see, we have like about 55 gigatons in 2015 that we emitted, and actually it has become more and more until 2020, although we try to go renewable. And in order to meet our climate targets, we really have to significantly reduce this in the next 10 years. In the next 10 years. Okay. Now, but this is CO2, right? And not all energy is CO2, and we are good at renewables, right? Okay, let's look how good we are really at renewables right now. Okay, here's a report. I was looking for some nice graphics, and this is the best I could find. So this is a report from the European Union, and so it's just European, sorry, but I think it is, well, if it is representative, we are lucky, but maybe it is not. Okay, let's have a look. Let's have a look. The rightmost bar is really the interesting one because that is the mean of the EU. And what the green bar shows is the percentage of renewable energy that we aspire to have 2030. So we aspire to have roughly a third of the energy coming from renewables. May I remind you, we need to decrease the performance here, the CO2 emissions. That means we need to decrease the overall renewables as well, because currently we are already, if you look at the blue dot, at almost 20%. In 2015, we were almost 20%. Now we are at the red bar here. Okay. So what does that mean if we look at the energy consumption and the percentage that computing makes in it, and then extrapolate this on the fraction of CO2 emissions from computing? And if I say computing here, I mean not just running the computers, but also producing new machines with the pace that we currently pursue, and the projected pace from 2020 to 2040. And if you look into this is really shocking, because what you see in 2040, we have almost 40% of the CO2 emissions just being a consequence of using the projected amount of energy that we currently do and will do in 2040 for computers in computing. So I doubt this is feasible, to put it mildly. I think this is a very British understatement. The German statement would be, oh my God, we're doomed, right? So this is the kind of thing that we have to bear in mind, right? We can't continue using the energy as frivolously as we do. Okay, what has this to do with high performance computing? Is this Bodo Scholz guy completely mad, or what is happening? Well, I think what you have to think about is we can no longer afford to utilize the hardware as short as we do. People replace laptops and desktops every, I don't know, 3, 4, 5 years. We are not able to continue doing that. We can no longer just expect, in 3 years' time to buy a new generation of GPUs that have TPUs and MPUs and PLLs and DSPs attached to them with non-volatile memory, everything new, and, this will solve all our performance problems. No, we won't be able to do this simply by looking at the CO2 emissions that this would cause. Damn. Also, if you look at, in particular, if you look at supercomputers and high performance computing, and you see I slowly get to the real core here, then you will see that we actually are not very good at utilizing our machines. And in particular, in high performance computing, very often we only utilize 10%, 15% of the real performance. Why is that? Well, we burn a lot of cycles in very bad code. So we have to do something about it, right? And at that point in time, I think, we all can make the bridge here in this community and say, hey, hang on. I think this is an old story, right? Isn't that the story that we have always been selling? Right? We have since, well, I dare say 20, 25 years, at least, if not 30 years, we have said, okay, we have to use this functional approach. And it is great because it is so beautiful, right? We have high-level abstractions that we start. That's very good because, you can be very effective in writing programs, which is also a very nice buzzword. You can go to industry and say, your programmers will have high productivity. That's a good thing. Right? And then we say, haha, once you have these high-level abstractions, and you can think of fold, map, and scan, and you name them. And if you look at most of the projects, at least that are presenting in the context of this workshop, they all kind of do this. They have different ways and different choices. But at the end of the day, it's the same idea. And then you have high-level transformations. And again, we trumpet the FP horn and say, haha, this is just possible because we have such a clear semantics, we are side effect free, and we can prove these algebraic properties, and this is a fantastic thing, the world is good, right? And well, yeah, there is a problem of finding out in which order we need to do these and which transformation we really should apply. But we use sophisticated cost models, type-driven. We use machine learning to do this, and then we have very sophisticated code generators. And this is fantastic. It is like the golden egg, because not only are the programmers predictive, but code becomes very portable, right? Because we can shift the code, we can manipulate the code, and we get high performance because we can adjust it to the target hardware. Ha-ha! So this is the perfect solution. And then what we do all the time is we demonstrate this, and we have seen this in the morning, for example, in the for example, in the lift talk, we said, okay, look, we can compete with Q-sparse, and that is great. This is a great sign. So if you look at this, and having this smart art on the right hand side of my slide is very intentional, because that's a typical view of the consultant's helicopter perspectives. Oh yes, you should do this, and then all problems are solved. Life is good, isn't it? Okay, I have been singing this song at least, and most of you maybe 1 or 2 years, fewer, or maybe the same time, for quite a while. 20, 25 years at least, if not longer, and others have been singing this song even longer than me. So why don't we have HPC world domination? So why aren't we there yet? That should be all trivial, right? Oh yeah, let's go back. So a few combinators, nice transformation, smart code generation, et voila, problem solved. Why isn't it there? Why don't we have it? Come on, it can't be that hard. 20, 30 years in the making. If you think Seisel, I think, was in the 80s already. They demonstrated that it's possible, but then they didn't get the funding. HPC and high performance Fortran had the same idea in essence. They just didn't call it functional programming, but it was a very similar idea. They promised this within 5 years, and then it disappeared. So what's the problem? And are we crazy? Are we just sitting on our horse and waiting for the horse to reach out for the carrot, which it will never get to? Should we go home and have a swim at the beach, or drink a nice drink, and forget about all this? What is it? Or is it really the Holy Grail? So I don't know, and I will definitely not give you an unbiased answer. I will try to give you an answer from the perspective of the experiences that mainly my personal experiences, but with the help of many students and collaborators in the context of single assignment COSAC. Yeah. And all the technical details you can find on our homepage, more or less. Those that you can't find, please feel free to contact me at any time and ask questions or discuss things. My key how should I say, slogan is it's all in the choices, right? The difficulties that you face depend on any choice that you make on the road. And there are more choices than one may have bargained for. And the most obvious choices are the language choices. So what are really your abstractions that you have? Is it a map? Is it a fold? Is it an IMAP? Is it a God knows what, right? What exactly is it? How many of those do you have? What are your assumptions about how you represent data? What is your type system? How do you deal with modules? What other language constructs do you support? Okay, then you have to decide how you transform. And there, woo, you have a plethora of choices as well. Do you flatten? Don't you flatten? Nest? Don't you nest? Do you bring it all in one particular form? Is that a good intermediate form? Is that not a good intermediate form? And unfortunately, to make things a little bit more spicy, any choice you make at any of these levels influences the potential choices that you have to make at other levels. Yeah. Why should it be easy? Yeah, you have choices in how do you generate the code. Do you optimize for data reuse? Do you optimize for temporal locality? Do you optimize for overall memory demand? Do you optimize for, I don't know what, for vectorization, or don't you optimize for vectorization? Okay. And when you start thinking about different targets, oh boy, you're in for a surprise. Because not a single choice fits all bills, right? Yeah, if some projects, essentially, I think all projects kind of focus on one primary architecture that they are interested in. And then they try to support the other architectures to some level. The problem is that the target choices are also rather wide, let alone the choice if you have heterogeneous systems with CPUs, GPUs, and different networks and supercomputers involved. And okay, so let's have a look at the choices that we've made in SAC and what, in my view, the consequences of these choices are. And obviously, I can't talk about all the choices, but I try to give a broad idea of the choices, of the key choices that we have made. Right. So overall, that's the basic setup that we have chosen. So when we started out in the 90s, in the last millennium, essentially we tried to get rid of anything that potentially would harm our performance. So we said, okay, no higher order functions. Yes, we love higher order functions, but no higher order functions. And in a way, I think this choice doesn't do our harm. It is a nuisance, yes, because if you start writing abstract programs, you would like to have higher order functions. But it's not a conceptual problem, because at the end of the day, what you can do is you can do defunctionalization. And for example, the FUTAC project very nicely demonstrates how this can be done. And how this is done. And there's a scheme-based project called Stalingrad in the US who demonstrated that 20 years ago. So it can be done. It is a matter of programming, essentially. Surely it has an impact if I try to sell my system to users, to end users, because they may say, okay, you say it's a functional language. Why don't you have higher order functions? That's impossible. Yeah, and I hear that. Yes, I hear it. But I don't think it's a conceptual problem. Okay, forget about that. Polymorphism. We don't have any polymorphism. Not nice. Very annoying. But again, I think it's a similar problem as with higher order functions. We would, if we were to support polymorphism, we would restrict it to a case where we demand that it can be specialized out. So we can make them all monomorphic. And then, so in essence, in a way, SAC is a core language. You can see it as a core language of a language that would support this kind of, I would call it pseudo polymorphism. Then we decided to have full recursion, and not all the other approaches do that. Some say, okay, you only have tail end recursion in the form of loops, but I think at the end of the day, the real difficulty in analysis remains whether you have full recursion or tail end recursion. And as long as you encourage the programmer to use tail end recursion, I think you'll be good. So I don't think that is a bad decision either. So far, I kind of, how to say, contradict myself in a way. Say these choices are not, in my opinion, not really relevant. Yeah? And please feel free to interrupt me and disagree with me at any point in time, if you have a good argument, that is. The first choice that is really important in SAC, important in the sense that it has consequences and not just minuscule ones, is the choice that we say we want to support n-dimensional arrays. Okay. Most people's reaction is n-dimensional arrays is just n-fold nesting of one-dimensional arrays, isn't it? Yeah, in principle that is true, but we have this idea that we would like to write programs that can take arguments that are arbitrarily deeply nested, and we don't want the programmer to require the programmers to specify recursion to do that. And if you want to do that, then you have to support a notion of an n-dimensional array where you don't know the number of dimensions statically, potentially, at least. Okay. And then we say, okay, we don't want actually crazily nested stuff. We just want to have homogeneous nesting. Okay. This was mainly motivated by the idea to make our life easy. Ha, little did we know. So we said, okay, homogeneous nesting only. That means if you have you can have an element vector where each element is an m by k array, and that means overall it's an n by m by k three-dimensional thing, and these are indistinguishable. You can switch between the view of the two. Okay. Now, if you want to have this, then immediately you have to pay for it. The first thing that you have to pay is actually a payback, and that is the shape of your thingies are now conveniently expressible by simply an n-element vector. So again, if you compare this to the lift talk in the morning, you know, we at this stage we are very constrained, and it's very simple to encode our shape now because it is just a vector of n integers, and that's it. There are no interdependencies between the shape components in deeper dimensions. Another price is that you can't any longer index by just scalars. So even if you have a vector and you say you want to select the third element, you have to provide a one-element vector to select the third element. Why is that? Well, if you want to have shape polymorphic programming, you don't know how many indices you need. So therefore, it needs to be a vector. Full stop, end of story. You can make this a different type, and that is yet another decision. And if you want to go the dependent type route, then this is something that you may want to do. But the basic thing is it has to be a vector. You can call it an n tuple if you want to, but essentially that's interchangeable. Now the good news is programs can be super generic. You can define APL operators in that language directly. Woo, sexy. The bad news is programs can be very generic. Generating good code for generic programs is a challenge because, you know, we have just widened the semantic gap. Okay. Okay, what are the choices then? Well, the first choice, the consequences then. Well, the first consequence is you really need to have an elaborate type system. Because you need to be able to express this. You need to be able to express the shape somehow in the type. And so in SAC, we have made the choice that we want to use subtyping and intersection types, because we didn't want to run into the difficulties that we may have to reject programs because the type checker can't prove that they are correct. And so that was our initial thinking, and it is also very convenient for programmers, in particular for end users. So we have over the years had various collaborations with industry, and they found this typing system very, in a way, refreshing, because it was very simple for them to understand. Right, so the end users could deal very well with it, and they were very afraid that it could be something really, really sophisticated. So that's good news. But the bad news is the formal side of this is a bit of a beast. And why is it a bit of a beast? Well, just look at the hierarchy of our types. So on the top level, we have what we call the AUD types. That means arrays of unknown dimensionality. It's just an integer array. We don't know anything. It could be a scalar thing. It could be a vector, matrix, a n-dimensional tensor. We don't know. Then on the next lower level, we know just the dimensionality, arrays of known dimensional, AKD. Here it's a scalar, it's a vector, it's a matrix, and so forth. There are infinitely many of these, potentially at least. And that has implications. Well, because subtyping with infinite hierarchies or with infinite lattices of types becomes interesting if you want to compile modules in isolation and things like that. But I won't dive into the details here. And then we have our most beloved types, the arrays of known shape, which are on the bottom layer here. And there we say, we know the exact shapes. And that's a beautiful thing, because that gives us a lot of information about generating good code. And so if you want to have real high performance, you want to have as much AKS in your program as you can. Okay, generic specification on the one side, that means you typically define in terms of this. High performance code on the other side means you really want to have this. There's just one way to get from there to there, and that is specialization. Okay, this is essentially what I would call the beauty and beast of generality. So let me throw some SAC code at you. Don't bother to understand all the details. In essence, what this is a generic addition of two integer arrays with the same shape, A and B. And this thing here is called the with loop. That is our n-dimensional construct for defining a new array of the same shape as of A. And we select individual elements in A and B at the corresponding position, add them up, and construct the result of it. So this is a super generic definition, and all of a sudden we have a function add that can be applied to any array you like. And if your dimensionality is 105, there you go, you can have it. It will work, provided the compiler generates correct code and that you have enough resources on your system. Right, and you can easily specialize that. So if you then have an application to two-dimensional things, then the compiler comes along and says, yeah, okay, we have a subtype here. This is the int22. It's an AKD subtype of int star. That's fine. And we can generate this instance, and we can here immediately see that it's a two-dimensional, and you can envision how it's easier to generate code for this. Okay, but I said, in general, what we would like to have is AKS. And yes, oh boy, you can do that too. If I see an application of the thing into a 3x5 matrix, then I can generate this variant. And this goes very well with the overall idea of intersection types in SAC, because this is just an ad hoc overloading. Whether you write it by hand or the compiler introduces it, doesn't really make a difference. Very nice. Okay, you have to be a bit careful. If you have too many of these, then maybe you have a code explosion problem. But in practice, this is almost irrelevant. Good solution, right? Okay, where there's a beauty, there's a beast. Here's the beast. This is a take function, as anybody can imagine. It's an n-dimensional take. So we have an n-dimensional array here, and the shape has n components, hopefully, and n element vector. And what this does generically, it essentially creates an array whose result shape is the argument SHP, and the elements are just copied over from A. Oh, that's good. That's easy, right? So let's specialize. Why not specialize? Okay, here we specialize. We apply this to a two-dimensional matrix here, and boom, boom, two-dimensional, result two-dimensional. Good. Why are we looking at this? Isn't that just the same as the previous slides? Okay, here we apply this to a two-element vector and a two-dimensional array A, and the result shape is it's an AKD type. So why is that? Well, it's simple, right? Everybody knows it. It depends on the values of shape. So we can't. I mean, we could specialize if we were to specialize for values, but hey, that would be okay. So here's a problem, and the problem only comes to light on second look, right? Because on first look it all looked beautiful when we are looking at add, and there's thousands of operations where the shape of the result only depends on the shape of the arguments. Here it doesn't, and there are just 2, 3, 4 APL primitives that have this property, but boy, they can kill your program. If you start writing programs like that, it is a pain. Okay, so I have this Pandora's box analogy here, and you see the further down we have to go with respect to specialization, and here I added a layer of value types as well, because you can do this straightforwardly. Then your non-termination or code explosion level goes crazy. Right, so let me speed up a little. So we have to kind of control specialization. And the good news is, if you dig a little deeper, you can develop a analysis which tells you how far you have to specialize in order to do things. Right? We called it the Specialization Oracle, but it was a pain. And here you see already, a choice made very early, namely to say we want to have this genericity, and on the other hand we want to specialize, requires us to do something. And it is painful. I can tell you it was painful. It was painful to develop it. It was painful to implement it. And it is painful to debug it when it goes wrong. No? Now, with this Specialization Oracle, our take problem is salvaged again. So here's our take. And then here's our Oracle. What the Oracle tells us is, it says, okay, if you want to have a result shape and you don't care what the shape is, well, then you don't have to care about the arguments. That's always true. But if you want to know the dimensionality of the result, well, then you need to know the dimensionality of both of the arguments. That's good enough. And that's the take case on the bottom that I was showing you. But if you want to know the shape of the result, then unfortunately, it's not good enough to know the shape of the first argument, but you need to know the value of the first argument, but not the value of the second. Right? So this is essentially always the most interesting part of this Oracle. What is it I need from the arguments in order to know about the result? And with this, I can steer the specialization, and I can actually say, okay, if you know the values here and we don't have too many specializations already, we can do it. We can get this done. So what's the conclusion about the choices made here? Well, it would be nice if you could annotate more. So we would like to have something a bit more towards dependent types, at least I would. But then the problem is, as soon as you want to go fully dependent, just imagine the kind of type signatures that we were seeing in the first talk this morning. I'm not so sure whether the typical users that we had exposed the system to from our industrial partners would appreciate that. Because the average domain expert still has to be able to specify the program. So I think actually what would be nice would be a bit more of a hybrid solution, where there is some help by the compiler, be it some form of inference. So I think this topic is far from being over. Another question is still the question, how far should you specialize, and what is really the impact of the code performance? Because there are some codes where AKS specialization is not really required. Yeah, okay. So some guidance there would be a nice thing to have. Another problem is that our nice genericity, I should say outcry for genericity, actually has led to the introduction of index vectors. Vectors means dynamic allocations, right? Unless we have special provisions in the compiler for it. Because a vector is just a normal array. A normal array is dynamically allocated and dealt with in a functional manner. So, okay. A small thing, it seems, but no, it isn't, because now we need to have a dedicated optimization that gets rid of this. Yeah. Where we can eliminate index vectors. So in fact, we have developed an optimization called index vector elimination. And what it essentially does, it says, okay, in this case, we can totally flatten the generators under the hood, and then we are just dealing with an offset, and this is just a scalar offset, and that can be statically done. But again, it is just, we are asking the question, why aren't we there yet, right? And here's one of the explanations. Because we need to do lots of things that are not totally obvious. The second choice that we have made, and you see it's just getting worse in a way. The second choice we have made is we express all data parallelism by one language construct called the with loop. The idea is you have a rectangular index space, which can be a grid, and then you have several grids from which you know that the union is exactly the entire index space of the array. And then we have different versions. What we do with the values once we have computed them, we can either generate an array or modify an array or fold an array, things like that. That is very nice because it keeps together the n-dimensional loop nests, and that means we have some better understanding over the entire task and the distribution of the work, in particular when trying to identify parallelism later on. That is very nice. What is very nice, optimizations and transformations can essentially just deal with one language construct. We don't have 20 transformations, and if we want to do something different, we have to add another 10. No, we only have one. Sounds beautiful, right, at that stage. The drawback or the price is the with loops can become very complex, right? We can have with loops that have 10, 12 different subsets of the indices where they do different things on. They can be arbitrarily nested. Dealing with these rather elaborate constructs is at times difficult, in particular if you want to be able to prove the correctness of your transformations. So I will very briefly and quickly, those of you that have heard about SAC most likely have heard about most of these optimizations, talk about the optimizations that we have developed to deal with this. We have three key transformations. First is what we call with loop folding. This is similar to what the Haskell world very often calls fusion. In essence, it's the idea to elide intermediate arrays. So here is I always think of these as being large arrays, right? So if you have D equals A plus B divided by 2, then if we inline plus and the division, then, and here I use a different notation rather than the with loop, which is a more recent addition to the language. It's just a short form of the with loop. Oops, a short form of the with loop. you can read it as a set comprehension or an array comprehension. For all index vectors IV, the result is A of IV plus B of IV. So this is how we create an intermediate array. Let's name it C here. And then, we compute the multiplication, which here is 2 times C of IV. What with folding in essence does, it just brings these together. It does a forward substitution of the definition of C into this, right? Now, this is totally trivial on this example, but it gets very, very funny if you have arbitrary index sets that you're dealing with here and we're dealing with there. Then you have to intersect index sets. It also becomes interesting if you do C of IV plus something or minus something, because then you have to project where these accesses go to. Technical details can be found in a paper, but in essence, this can be done. And this is, I think, the most crucial transformation that we have. Then we have with loop scalarization. So at times you end up with funny codes. And one funny code that you could have is, for example, a code like this. You could end up with having an addition of rows here of a 2-dimensional thing, which are then being added up by themselves. So we end up with an element-wise addition in reality. And obviously, in order to get folding apply as often as possible, one of the things we do is we always try to suck these into a single with loop. So we figure out that actually these are equivalent. The last one is with loop fusion, and that again has something to do with this idea. Any n-dimensional iteration, data parallel operation, is expressed by with loop. If we have several with loops that iterate over the same iteration space, it makes perfect sense to join these, because you have improvements on temporal locality and things like that. So in essence, what this means is, once you do these, then you can fuse them into a with loop that has returns 2 arrays from 2 argument arrays. And that means just they share the iteration space. Again, this looks totally trivial. It is not once your generator sets become way more complicated. If you're interested in details, again, this lives somewhere else. Now, you may wonder why this is called with loop fusion. Well, this is called with loop fusion because it is essentially the same as doing loop fusion in the imperative world. And that's why this is called with loop fusion. Okay. Now, when you want to generate code, you have to make choices again. Right, and so all the choices that we have made initially were based on common wisdom on how to make sequential code fast. Because first of all, we needed to demonstrate that you can even get close to sequential performance. Because why bother with parallelism if your sequential performance is factor 10 out, right? So then you have to do lots of things. You have to avoid branching in the innermost loop. You have to maximize locality, and then you have to think about whether you should have flat or non-flat index generators, and this later decision depends again on what kind of index accesses you find on the inside. It's non-trivial, and it took us a bit of a time to really figure this out how to do. And I think we have a reasonable state that we have reached there. So I'll try to speed up a little so that we can make it in time. Now, when we then said we want to do multi-threaded execution, then the first problem that arises is you have to choose the level of parallelism. We all have to do this. I mean, we are blessed because we have the data parallelism there. That means we have parallelism galore, but we have to choose. We have the freedom to choose. And here, it is really nice to have this n-dimensional representation. So we don't have to I think Futag, for example, does something like incremental flattening. We don't have to do any of this because we have the n-dimensional nesting available, and then we say, okay, we just do the outer 1 or the outer 2 or the outer 3. And also the shape specialization here really pays off, because if we know how big the iteration spaces are, these decisions are easier to get right. without having to resort to some empirical testing or optimization in time. Last not least, the multi-thread backend is actually quite, how should I say, lenient in requirements, because most of the optimizations that you do for the sequential backend are good for the multi-thread backend as well, because, yeah, well, in the multi-thread case, you have sequential engines that are running, you have coarse grain, so that's a good thing. So going multi-threaded it is a lot of work, and there's lots of further details that need decision, and there is again papers on this, how we have achieved this, but that is doable. Then what happened is we said, okay, we want to, we have this here goal that we say, we want to have different backends, different architectures, all has to work fine. So the next thing we were looking at, obviously we couldn't miss out on the GPU hype. Okay, so first thing is, okay, we have to identify which goes where. Which array lives on the host and which one lives on the device? And when are these communicated? And how are these communicated? Oh God, there's no notion in our programming language about memory or memory locations. Okay, to automate these decisions, one of the things that we can do is we can piggyback on the type system. That's good, because the type system gives us shapes, gives us information, and so we may be able to do this. And then, you have to figure out, how do you optimize transfers? So what happens in loops? Can you keep data on the GPU, or when do you really have to transfer things? That is all not exactly trivial, as you can imagine. Likewise, you have to identify kernels. This is kind of the same as figuring out what it is you want to do in parallel. Now, the difference is the choices here are different from the choices that you want to do in the multi-threaded version. Okay, why? Well, kernels they like fine grain. That's great, because they want to have homogeneous computations. They don't want to have conditionals, and they don't even allow for all kinds of operations in there. Okay, again, you can piggyback on the information that you have. So having the n-dimensional information available and having shapes available is a big gain. But it is still a lot of extra work, which is kind of orthogonal to the other work that we've been doing. All these high-level transformations that we did in order to fuse and fold with loops still has to happen. But the problem is, you may want to reconsider certain of those decisions, because it might be cheaper to recompute things rather than load things from memory again. Ugh. Horrible. And then, when we started looking into this, it really felt like the empire is striking back. Why? What is happening? Well, what is happening is, for example, when you have grids, interleaved grids on which you want to compute, then in the sequential backend you want to have temporal locality, yeah, and that means you want to interleave your grid computations. If you have a kernel, you don't want to do this, because you want to have two separate kernels that do this. But this is a fundamental change in the way you generate the code. So our intermediate stage of the optimized with loops means we have to break off now and generate different code from the GPUs. And there are hundreds of trade-offs. A few of the trade-offs we've been talking about in the paper 5 or 6 years ago, and we still do not quite know. And we hope that some machine learning supported automated tuning could help, but we have not really looked into this yet. Then we come to memory management. Memory management, again, you have choices that you can make. where you have to decide what you want to do. So we have decided we want to have flat array representations in memory. That has many advantages with respect to memory access patterns. It's also one of the results from the CISA project in the 80s that they said nested representations in memory are not exactly a good idea in terms of high performance. So then the question was, okay, how do we make sure that we can reuse and update in place? And the very natural choice here that is screaming at you is reference counting. You know? When we don't want to do stop the world garbage collection, no, but we want to, make sure that we can update whenever we have unique access. We don't want to enforce this on the programmer, so we don't want to require the programmer to make sure that an array is in fact unique. We want to do this under the hood. We infer whether it's unique or not, and then we decide whether we need to make copies, and where we can't statically infer it, we dynamically check. And that is a very good strategy, in particular, when having flat array representations. That means you have very little reference counts. We don't have any cyclic references. So it is, the nirvana of reference counting, you could say. Oh, that's great, fantastic. So the challenges await you when you have nested with loops and things like that. But, this can be dealt with. And this paper is one good way. Now, if you go multicore, and I have slipped this slide in the break because it kind of reminded me of, or it gives a potential answer to one of the questions that you posed to Phil. If you have a single-threaded computations, then this is the flow of computation here, and then you do some reference counting operation on some arrays that you're dealing with. In essence, if you call a function with an array, then you increase the reference count, and whenever you use it inside the function body, you decrease it, and so you have an up-to-date reference counter. That's fine. If you have a data parallel program, then the good news of the data parallel program, in contrast to what the task parallelism that the Haskell guys do, if you have a data parallel program, then what happens is from the sequential case, you go into the parallel case. And in the parallel case, you have multiple threads, and the multiple threads want to do reference count operation. But what kind of reference count operations do they do? Well, first of all, they might allocate arrays. If they allocate arrays, the good news is arrays can't escape the scope of the data parallel operation. This is guaranteed. Woohoo! Functional semantics, I love it. Right? And that means I can have a thread local heap here. That means I can do reference counting here and there at the same time, and it doesn't hurt me. I don't even need to have a lock on it. Oh, well, hang on. What is with the relatively free variables? Oh, yeah, there is the relatively free variables. But what is a relatively free variable? It's an array that exists out here and which is referenced inside there, most likely by almost all of the threads. What this means is I can only reuse this global thing in one out of the n cases if I have n-fold parallelism. That price is too high. So what we do is we simply turn reference counting on relatively free variables off while we are in the data parallel section. And if we do so, the good news is we don't need to lock, because we know that reference counting is only happening thread local ever. That's beautiful. That's really beautiful. And we end up with what we call bimodal reference counting, right? So reference count either works as usual, or when any object goes into as an argument is a relatively free thing inside a fork, which means essentially with loop execution, then we turn the reference counting just off. So if anybody wants to do a reference counting operation, it just says, oh, it's in no RC mode, forget it, I'm not doing it. Simple solution, very nice. So reference counting, fantastic, right? Then we ported the entire thing to the GPU. What can possibly go wrong when going to a GPU? Well, in essence, it turns out reference counting is not the only problem, but it matters how many allocations you do. If you want to have the best possible transfer rates, you need to minimize your memory allocations, because allocating memory on the GPU is costly if you want to have asynchronous transfers, and they are more efficient than the synchronous transfers. I leave you some references here, so if you're interested, just follow it up on this. And then the story goes on. The more architectures you look at, the more fun you detect. If you want to do vectorization, you want to fiddle with data layouts and distributed memory, you have to have other support for things. We have looked at massive multiprocessor systems on chip. And again, the code generation is vastly different. Even the transformations on a higher level become painful. If you're interested in the details, please do go to our homepage or just drop me an email and ask, and I can point you to the relevant things. So let me try briefly to get to the conclusion. So what is now about this carrot? I think we do come closer to the carrot because we find solutions, but we really have to be patient. We have to be way more patient than anything that has been done before. If you look at high performance Fortran, 6 years, that's ridiculous. 10 years, it's ridiculous. It needs a lot of time. And anybody who is trying to do this knows that it is way harder than it seems. And if you win a single battle, right, or a single hill, that doesn't mean it works for the next example, right? Because we have to explore these design spaces in detail. And to explore them means you have to bring all the optimizations together to really see what the impact is. And I think there's one thing that I would really like to see happen more, and that is we need to have more cross-project comparisons. We need to figure out, if you make a certain choice in the design, and I try to outline a few of the choices that we have made, what is the real impact? It's not measuring how fast someone is or isn't on a certain example. It is about, what are the consequences of these choices? An honest discussion about, what aspect of the design that I'm looking into really sucks because, it creates problems at this front, and does the other approach possibly help me on this front or not? And that is something that I would like to see. I still believe that functional high-performance computing is the key to low-carbon computing. We just have to bring this patience to the table. And I think a good sign to this is if you look at the imperative world, you see that things are getting closer together very slowly, but it is moving. So I'm not yet the desperate rider of this horse. I still believe in the carrot. Thank you.
Thank you very much, Pandoras. We do have time for a few questions, and then I think we can also continue in the lounge. There should be the FHPNC table. So for the questions again, if you could type the questions in the Q&A tab of the conversations. Maybe in the meantime, we're waiting for more questions. Pandoras, you mentioned basically that like with dependent types, you should be really careful what you ask for because it's nice and fancy and you can do a lot of things. But on the other hand, it's very easy to make it too complicated for the users, like your industrial users. So I was wondering, do you actually have a wish list from these users, what kind of features they want?
They mainly, that's very difficult to say. And, you never talk to all the users in the world. That's the first problem. It really depends on the field of applications that you're talking to. I would use a slightly different approach. I would look at what people do use. And you see that people use systems that are easy to program. Python is a wonderful language because it gives you the freedom. You can just do something and then see what happens. People use MATLAB, and you have almost no guarantees there. I hope there's no MathWorks employee in here, or if he is, speak up. No, and I think that there is the problem. It needs to be easy to specify, and it needs to be intuitive to be understood. If people have to learn how to introduce pi types, I don't think this is possible. At least not, you know, on an intermediate level, this may be fine. This may be great, but not for the end user.
Federico Pizzuti has another question concerning the unpalatability of dependent types to users. Do you believe it is because they require too much information to be provided, or is it due to the way the information is encoded that is the scary types?
Yeah, if I would know the total answer to that, that would be great. I think it's a combination of the two. I think that we could find ways to make it palatable in the way how we specify this. And if you look in the developments in the gradual typing of the record system, I think they do very good stuff in that direction, where you can annotate a little bit, but the type system will not immediately kick you off the board if it can't satisfy everything statically. And I think that should be the route we should go. Which doesn't mean one shouldn't go dependent types at all. I mean, I think it is fantastic if you can prove these things. But I'm not sure how to separate this from the ordinary user. And a good answer would be very much appreciated.
And I think Centrals has another question, basically. So in hindsight, what do you think are the largest mistakes in design implementation approach?
Largest mistake. I think it is we repeatedly make the same mistake, and that is that we always start from the easy case and then try to widen it in hindsight, and that makes it difficult. So to give an example, in the beginning we said everything needs to be AKS. The world was beautiful, it was easy. And then we said, oh no, we really want to have modules. Oh no, we really want to have generic functions on the modules. And then, you know, the entire subtyping business came and that was painful. Is it a mistake? I don't know. I would love to know. I would love to learn whether it was, for example, a mistake to have this idea of keeping the n-fold nesting. Because if you know it, look at FUTAC or lift or accelerate. I think, if I'm not mistaken, essentially you always look at an n-fold nesting of your one-dimensional maps, right? And so you're dealing with nestings of maps. Whether that is more convenient or not, I don't know. We have examples where we're dealing with grids and coarsening and widening of grids, and I can't really see how that would compare. I would love to do that. I would love to find this out.
Yeah, Accelerate also has this basically shape polymorphism in, but because there are other restrictions in the language, I think the problems are slightly different. But one thing I really liked, you mentioned in the end, and I think we should pick that up later on in the discussion, is that we should really come together and talk about the pros and cons of our design choices. Because as you said, like, it's such an incredibly difficult problem. And I think we could learn a lot by talking more about what kind of design choices we made, what the implications were. And so I would really love to pick that up later in the last session today. Then I would like to thank you again for this excellent talk. And as I said, let's meet back on the FHP, and we have to find a shorter abbreviation. I always struggle with the name of this workshop. So let's meet back in the lounge for more questions.
Yeah, thank you. See you in a bit. How do I get there? Interesting question. Looks like I have to. No.